Okay, so when we talk about keeping information safe online, it feels huge. How do we actually know things are secure?
Right. It's not magic. It comes down to some core cryptographic tools, things you'd find in, say, standard libraries developers use.
Like NodeJS's crypto module, perhaps.
Exactly like that. Provides those fundamental building blocks.
So let's try and unpack some of those today. We're thinking about things like hashing, HMAC, encryption, signing, the basics.
Yeah, the goal is to get a handle on what they are, why they matter,
Mm.
especially if you're building applications or just dealing with data security day to day.
Makes sense. So these modules give developers cryptographic power without needing a math PhD?
Pretty much. They handle the complex math. Let's start with maybe the most fundamental
Hashing.
hashing. Okay, what's the gist?
Take any data, could be tiny, could be massive, and run it through a hashing algorithm. Out comes a fixed size string, that's the hash, or sometimes called a digest.
Like a fingerprint for the data.
That's a great analogy, yeah. Digital fingerprint.
And what's that fingerprint used for, mainly?
Yeah.
Primarily checking data integrity. Did this data get changed? You calculate the hash, send the data and the hash.
And the receiver hashes it again.
They hash the data they received. If their hash matches the one you sent, the data is likely untouched. Change even one bit.
And the hash totally changes.
Right.
Sensitive.
Very sensitive.
Yeah.
And good hashes are designed to be one way. You can't easily get the original data back just from the hash.
Okay. Irreversible.
And collision resistant, meaning it's incredibly hard to find two different inputs that somehow produce the exact same hash output.
Gotcha. We see things like SHA-256, SHA-512 often.
Those are the common secure ones currently.
But we should probably steer clear of older ones like MD5.
Absolutely. MD5 is considered broken for security uses. Don't rely on it for anything critical. Seriously.
Okay, message received. So hashing is for integrity. What about passwords? This seems like a place you really can't mess up.
It absolutely is. And the number one rule, never just hash the password directly.
Why not? Seems like the obvious first step.
Because of rainbow tables. Attackers have these huge pre-calculated lists of common passwords and their corresponding hashes.
Ah, so if your hashed password is in their list.
They know the original password instantly. Game over.
So how do we defend against that?
We use something called assault.
Salt, like table salt.
Sort of. It's unique, random data generated for each individual password.
Okay, so every user gets their own random salt.
Exactly. You combine that unique salt with the user's password before you hash it.
So even if two people use password 123.
Their different salts mean their stored hashes will be completely different, which breaks the rainbow table approach.
Clever, like a unique secret ingredient for each hash. And for passwords, we should use specific algorithms, not just SHA-256.
Yeah, definitely. Algorithms like Ardon2, Script, or bcrypt are recommended. They're designed to be slow.
Slow? Why would you want slow?
They're computationally expensive. They deliberately use more memory or CPU time. This makes it much harder for attackers to rapidly try billions of password guesses against your database. It slows them way down.
Makes sense. Security through, well, slowness. So the process is generate salt, combine with password, hash it, then store both the hash and the salt.
Correct. You need the salt later for verification.
Right, because to check a login, you get the stored salt for that user, combine it with the password they just typed in, hash that, and then compare that new hash to the stored hash.
Precisely. That's the secure flow.
Okay, so hashing gives integrity, but what about knowing who sent the data? Authenticity. That's where HMAC comes in.
Exactly. HMAC stands for Hash-Based Message Authentication Code. It's still a hash, but it adds a secret ingredient.
A key.
A secret key, yes. A secret key that only the sender and the intended receiver should know.
So it's hashing, but with a password, essentially.
Kind of. The key ensures that not only is the data unchanged, integrity, but it also came from someone who possesses that secret key, authenticity.
So it provides both integrity and authenticity. How does that work?
You calculate the HMAC using the data and the secret key. Send the data and the HMAC. The receiver uses the same secret key and the received data to calculate their own HMAC.
And if they match.
They can be pretty confident the data hasn't been tampered with and it came from someone who knows the key.
Like a tamper-proof seal that only you and the recipient recognize.
Perfect analogy. Now, we also briefly touched on encryption-decryption.
Right, that's about confidentiality, keeping the data itself secret.
Yes. Symmetric methods like AES use the same key to lock and unlock. Asymmetric, like RSA, uses a public key to lock, private key to unlock.
And related, signing and verification. using those public-private keys to prove origin and integrity, like a digital signature.
That's the one. Proves who sent it and that it wasn't altered.
So lots of powerful tools here, but the takeaway seems to be use them carefully.
Extremely carefully, especially for things like passwords or secure channels. Implementing crypto correctly is hard. Use well-tested libraries, understand the principles, and maybe even consult experts if it's critical. It's easy to get wrong with serious consequences.
So understanding these fundamentals, hashing, HMAC, salted password hashing, the basics of encryption and signing, it's pretty crucial for anyone building software or handling data today, right?
Absolutely. It helps you understand the security layers, make better design choices, and appreciate why things are done certain ways. It's foundational knowledge for secure development.
And it's a field that's always changing, isn't it? New threats, new algorithms.
Constantly evolving.
Hmm.
These building blocks are essential, but the landscape shifts.
Which kind of leaves us with a final thought to chew on. How might something on the horizon, like, say, quantum computing, potentially change everything we just talked about? Could it break these fundamental tools?